In this demonstration, we're going to show how a container of ice water, which is stabilizing at around 0 degrees Celsius, which is normal for a solution of ice water, is going to exhibit the effects of the heats of solution. Normally, when you dissolve a salt in water, the energy that is needed to break the bonds of the salt come from the heat that's in the water. So what we should observe if we add some salt to this ice water bath is that the temperature will suddenly drop as the salt dissolves. And I'll do that. I'll hand over the phone so somebody can film it. So I'm just going to take some table salt, sodium chloride. I'm going to add it to the solution. That should be more than enough because it'll be saturated anyway. And if you keep an eye on the thermometer as the salt begins to dissolve, you should notice that it starts to drop. I'm stirring with a thermometer, which is not exactly good laboratory technique, but I couldn't find a stirring rod. We'll just do it very gently. Notice how the temperature is already dropping to sub-zero. Mm-hmm. Of course, the presence of the salt prevents it from freezing because it probably interferes with the formation of the bonds. If you were to chill water below the freezing point, it would you might be able to supercool it if the water was pure, but it would then suddenly form a crystal, as you sometimes see on the windshield of your car on a cold morning. You'll see ice crystals forming and racing across the windshield when you put water on the windshield, or if you don't have good windshield washer fluid, or if it's a particularly cold day. We see the temperature is already down to 4 degrees below zero, and if you keep on stirring, the temperature will eventually drop to about minus 11 Celsius. As more and more of the salt dissolves, what's happening is as the sodium chloride breaks down, there's a certain amount of energy needed to break down the lattice of the sodium chloride. That energy is being robbed from the water. It's an endothermic process, and because the salt is immersed in a solution of water, the heat energy ends up coming from the water, which ends up being chilled. So we see the temperature has already dropped to minus 6 or minus 5.5. We'll just keep on stirring, see just how low we can get it to go. And if the temperature goes below zero, the ice isn't going to melt anymore. So the presence of the ice was simply to ensure that the water temperature would be at least at zero. Because whenever there's a phase change going on, if you have a mixture of two phases of the same substance, you get an arrest in the temperature change. So water will warm up to zero if it's salt, if it's ice, and then while it's melting, the breakage of the bonds in the ice helps soak up the extra heat energy. So melting ice water will stay at 0 degrees Celsius until all of the ice has melted. And then once it's all water, the water will start warming up from 0 to the next point where it'll stop changing temperature at 100 degrees Celsius. At 100 degrees Celsius, then the water will start boiling. And it'll stay at 100 degrees Celsius until all the water boils away and turns into steam. Those two changes, those two phase changes, and the energy that it costs to go through the phase changes are called the delta H of fusion for melting of ice and the delta H of evaporation to go from the liquid phase to the gas phase. And the same amount of energy is released if something in the gas phase turns into a liquid, except now the energy flow is in the opposite direction. So when steam condenses into water, it releases all the heat energy that it was carrying. You see the temperature is now gotten to minus 7.5. And it would continue to drop to about minus 11. similar reactions, well, it's obviously not sodium chloride in water, but there are reactions that are endothermic, which are used in cold packs, those kind of packs that you can apply to an injured elbow or knee by cracking it open. And then what happens is the bag is sealed with two chemicals in the bag. By cracking it, you cause the two chemicals to mix, which causes the temperature of the mix to drop down. You can also have reactions that when you mix the chemicals, it warms up. And so you can get heat packs, the kind you put in your mitts when you go skiing to keep your fingers from freezing. Now we're at -8. And we're still dissolving salt crystals, and the temperature continues to drop as it robs the heat energy from the water. We'll stop it there, I think. We've proved our point.